4.25 light-years. In the language of everyday distance, that number is essentially meaningless. It does not map onto anything a human being can feel. But here is what it represents. The gap between our solar system and the nearest star to our Sun, Proxima Centauri, is so vast that light itself, traveling at 300,000 kilometers per second, takes 4 years and 3 months to cross it. Nothing in the universe moves faster than light. And light, by that measure, finds the journey long. We have known about Proxima Centauri for just over a century. We have known for less than a decade that it hosts at least one planet orbiting within its habitable zone, the region where liquid water could exist on a surface. That planet, Proxima b, sits roughly the same distance from its star as Earth sits from the Sun. The conditions are not confirmed as hospitable. But the possibility is real enough that the scientific community treats Proxima b as one of the most significant targets in the search for life beyond Earth. So the question follows naturally. Can we get there? The honest answer is no. Not with anything we currently know how to build. And understanding why requires sitting with some numbers that are genuinely difficult to absorb. The most distant human-made object in existence is Voyager 1, launched in 1977. It has been traveling for nearly 5 decades. It moves at approximately 17 kilometers per second, fast enough to cross the continental United States in under 4 minutes. By any terrestrial standard, it is extraordinarily fast. At that speed, it would take Voyager 1 roughly 76,000 years to reach Proxima Centauri. And it is not even headed in that direction. 76,000 years is not a travel time. It is a geological epoch. It is longer than modern humans have existed as a civilization. The speed that feels remarkable within our solar system is, on interstellar scales, essentially standing still. To reach Proxima Centauri within a human lifetime, within a single generation, would require speeds on the order of tens of thousands of kilometers per second. At 10,000 kilometers per second, roughly 3% of the speed of light, the journey would take about 130 years. At 25,000 kilometers per second, closer to 8% of light speed, the transit drops to around 50 years. Both figures sound closer to plausible. Neither is close to achievable with current propulsion. The reason conventional rockets cannot get us there is not engineering timidity. It is the rocket equation, the same unforgiving mathematics that shapes every discussion of spaceflight. Chemical propulsion works by burning fuel to generate thrust. The faster you want to go, the more fuel you need. The more fuel you carry, the more mass you must accelerate, which requires more fuel still. The relationship compounds exponentially. To accelerate a spacecraft to just 1% of the speed of light using chemical rockets would require a quantity of propellant more than 1,000 trillion times the mass of the spacecraft itself. A vehicle with the mass of Earth carrying a payload of a few kilograms. The number is not an engineering challenge. It is a category error. Chemical propulsion does not scale to interstellar distances. This means reaching Proxima Centauri requires abandoning the propulsion paradigm that has taken us everywhere we have ever gone in space. It requires thinking in fundamentally different terms. And several research programs around the world are now doing exactly that, with varying degrees of credibility and varying timelines to anything operational. Ion and plasma engines represent the most mature alternative. Already used on missions within the solar system, these systems generate thrust by accelerating ions electrically rather than through combustion. They are far more efficient than chemical rockets across long durations. They are also low thrust. They push gently but continuously, building speed over months and years rather than minutes. Their limitation for interstellar travel is that even at their best projected performance, a mission to Proxima Centauri would still take on the order of tens of thousands of years. Better than Voyager. Not meaningfully closer to useful. Nuclear thermal propulsion, using a fission reactor to heat propellant and expel it at high velocity, offers a step up in performance. It has been studied since the 1960s, tested in prototype form, and never flown in space. Credible designs could reduce Mars transit times significantly. For Proxima Centauri, the numbers remain deeply discouraging. Travel times in the range of 40,000 years. More speculative, but genuinely studied, is nuclear pulse propulsion. The concept developed under Project Orion in the late 1950s and early 1960s. The principle is straightforward and spectacular in equal measure. Detonate a sequence of nuclear explosives behind the spacecraft, absorb the blast on a massive pusher plate mounted on shock absorbers, and convert each explosion into forward thrust. Theoretical analyses using fusion rather than fission warheads, far more energetic per unit mass, suggest that a spacecraft of enormous scale, perhaps 400,000 tons with a pusher plate 100 meters across, could reach speeds sufficient to arrive at Proxima Centauri in roughly 150 years. That figure is in a different category from the alternatives. It is still multiple human lifetimes, but it enters the range where concepts like generation ships, vessels where crews are born, live, and die across the transit, become at least imaginable as engineering problems rather than impossibilities. The political and legal obstacles to nuclear pulse propulsion are as significant as the technical ones. The partial test ban. Treaty of 1963 prohibits nuclear detonations in space. Any serious development program would require renegotiating frameworks that exist, in part, specifically to prevent what Orion would require. That is not an insurmountable obstacle over a long enough timeline. It is a real one. Solar sails offer a different approach entirely, one that requires no onboard propellant at all. The principle rests on radiation pressure. Photons carry momentum, and a sufficiently large, sufficiently light reflective surface can be pushed by sunlight. The Japanese Icaros probe demonstrated this in 2010 on a small scale. For interstellar travel, the geometry of the problem demands that the sail be deployed close to the sun, where radiation pressure is strongest, then use that initial acceleration to exit the solar system on a fast trajectory. The engineering constraints are severe. The sail must be enormous, extraordinarily thin and light, and capable of surviving temperatures of thousands of degrees during the close solar pass. Projected transit times to Proxima Centauri using solar sail concepts alone range from 1,000 to 2,000 years. Not a solution in isolation. Where solar sail thinking becomes genuinely interesting is in combination with directed energy, specifically laser arrays. Rather than relying on the sun's diffuse radiation pressure, a laser sail would be driven by a concentrated beam from a ground or space-based array, delivering orders of magnitude more force to a much smaller sail over a shorter acceleration period. The spacecraft would reach its cruise velocity quickly, then coast across the interstellar gap. This is the architecture at the center of Breakthrough Starshot, a research initiative announced in 2016 with funding from the Breakthrough Prize Foundation. The concept targets a fleet of gram-scale probes, wafer-thin spacecraft a few centimeters across, each carrying a miniaturized camera, communication laser, and power source, attached to similarly tiny sails. A ground-based laser array with a combined output of roughly 100 gigawatts would illuminate the sails for a period of minutes, accelerating each probe to approximately 20% of the speed of light, 60,000 kilometers per second. At that velocity, the probes would reach the Proxima Centauri system in approximately 20 to 30 years. Signal return from the system, traveling at the speed of light, would take another 4 years. The numbers are striking enough that they deserve careful examination. 20% of light speed is roughly 10,000 times faster than Voyager 1. The probes would be traveling so fast that interstellar dust, sparse but present, poses a meaningful collision risk. At those velocities, a grain of dust the size of a sand particle carries the kinetic energy of a rifle bullet relative to the spacecraft. Starshot's response to this is scale. Launch thousands of probes accepting that a significant fraction will be destroyed, and rely on the survivors to complete the flyby and transmit data. The laser array required ground-based, coherent, steerable, operating at power levels that do not currently exist in any single installation, is the central engineering challenge. Nothing remotely close to it exists. The research program is real. The hardware is not. The project's leaders have been consistent about the timeline. With sustained funding and no major unforeseen obstacles, a demonstration mission might be possible within 2 to 3 decades. The interstellar mission itself would follow after. What would such a mission return? Each probe, during its brief flyby of the Proxima system, would have minutes, perhaps less, to observe Proxima b. At flyby velocities of 20% light speed, there is no slowing down, no orbit insertion, no extended observation campaign. The data would be what can be gathered at extraordinary speed during a single pass. Images, atmospheric spectra, if the instruments and geometry cooperate, magnetic field measurements, whatever a gram of sensors can capture in the time available. It would be, in all likelihood, the most scientifically consequential few minutes in the history of space exploration. Even if Proxima b turns out to be barren rock, no atmosphere, no water, no sign of anything biology would recognize, the value of direct observation rather than inference from light years away would be transformative. And if the data suggested otherwise, the consequences for our understanding of where life exists in the universe would be difficult to overstate. Carl Sagan spent much of his career arguing that the question of life beyond Earth was not a matter of idle curiosity but of orientation, that knowing whether life was common or rare in the universe was among the most important facts a civilization could possess. He was not wrong. And Proxima Centauri, with its orbiting world at the right distance from its star, is the nearest place where that question might begin to be answered by something other than inference. The technology is not ready. The laser array does not exist. The gram-scale probes are at the research stage. The funding required, billions sustained over decades, has not been committed. Every one of those gaps is real, and none of them should be minimized. But the physics are sound. The concept is not science fiction in the pejorative sense. It is science fiction in the original sense. A proposal that extrapolates from real principles toward a goal that is not yet achievable but is not forbidden by any law of nature. That distinction matters. There is a difference between what we cannot do yet and what we cannot do at all. 4¼ light years. The nearest star. A planet in its habitable zone. And, for the first time in human history, a specific technical proposal for how a human-made object might cross that distance within a human lifetime. We are not there, but the direction is no longer entirely unclear.